Hello, my name is Vibhav Chinta from Marquette High School. The research topic and study that I did was a comparative analysis of durability among PETG and ABS plastics and 3D printed knee socket prosthetics. For some significance, in the United States, 1.6 million people are living with lower extremity amputations. This number is projected to rise to 3.6 million by 2050. This rising number shows how important it is to innovate and discover solutions within the field of prosthetics to combat the rising number of amputees. For some background, a prosthetic is an artificial replacement part of your body. It replaces a part that's missing. And 3D printing is a method of making a physical object from a three-dimensional digital model. A breakthrough in 3D printing could enable access to personalized prosthetic devices anywhere in the world, going to show how important it is to discover innovations not only within the field of prosthetics, but also 3D printed prosthetics. For some background on the plastics, first off is ABS, or acrylonitrile butadiene styrene, which has been used in the fabrication of various biomedical devices by 3D printing. It's widely used. Next is PETG, or polyethylene terephthalate, which has been shown to possess the strength necessary to support weight in prosthetics, making it a viable option for prosthetics. ABS and PETG are ideal for prosthetics. ABS has a tensile strength of 43.8 MPa, meaning it's suitable for structural applications, whereas the tensile strength of PETG is around 50 MPa, creating initial conclusions that in terms of tensile strength, PETG was stronger than ABS. Lastly, ABS is tough, resilient, and easily moldable. These reasons show why ABS and PETG were ideal for the study. In terms of prior research, per Marinopoulos in 2022, a study was conducted that looked at 3D printed lower limb prosthetics but only structural integrity, not the overall material durability. Next, a study by Romley in 2022 looked at 3D printed prosthetic leg sockets again, but only looked at the reinforcement materials were applied as well. Specifically, resins and coatings, and mechanical durability and strength was examined, not overall material durability. Then that brings me to the research gap. There's been a lack of research comparing two different types of 3D printed prosthetics. There's been comparisons of original prosthetics and 3D printed prosthetics, but not two different types of 3D printed prosthetics. Next, little to no research looks at the plastics individually. They look at the plastics with enhancements such as resins and coatings. Additionally, research so far examines structural or mechanical durability. It doesn't necessarily look at the big picture, the overall material durability. Bringing me to the research question developed: how do PETG and ABS plastics compare in terms of material durability when used in 3D printed knee socket prosthetics? First, let's move on to the methodology, where a knee prosthetic socket 3D printable file was downloaded from Colts 3D. Then this file was processed in the 3D printer software Ultimaker Cura. This file was then printed using an Ultimaker S7 Pro printer, and the following constants were kept. For each prosthetic printed, the brand Polymarker was used for ABS and PETG filament with a length of 2.85mm filament. Additionally, a 50% infill and a hexagonal pattern was implemented, meaning within the actual plastic itself, it was 50% full, meaning a 0% infill would mean that within the actual structure of the plastic, it was 0% full. The first test conducted was a thermal resistance test in the warm variant. This test revolved around placing each prosthetic in an incubator for 24 hours at 103 Celsius to examine the hardness values before and after. The same test was conducted in the cold variant, where each prosthetic was placed in a freezer for 24 hours at -10 Celsius degrees to see how exactly the cold temperatures affected the hardness values. An abrasion test was also conducted. Sandpaper grits of number 40, which is coarse, number 80, which is smooth, and number 100, which is fine, was rubbed on 3 distinct parts of the prosthetics, and the mass lost was measured. A water absorption test was also done. Water absorption percentage was measured within this test. Each prosthetic was placed in a plastic tub for 24 hours. The red circle shows the actual hexagonal infill, the actual plastic structure. As you can see, the blue dot represents water. And in terms of ABS and PETG, the blue dot is a lot more potent in PETG, showing that in terms of this test, PETG absorbed more water on average. In terms of calculate water absorption percentage, the mass after the water absorption and the mass before was subtracted and then divided by the initial mass and multiplied by 100. The next test was conducted was a drop test to test impact resistance. In this test, the number of drops was calculated and it was measured. Each prosthetic was dropped from a height of 9 feet, and as you can see, each prosthetic tended to bounce up, but PATG bounced up higher than ABS did. The last test conducted was a tensile strength test, and for this, each prosthetic was wedged within the grooves of a Irwin hand clamp, and the Irwin hand clamp was pressed until each prosthetic deformed. Then, using a caliper, the horizontal displacement of the top lips of the prosthetic were measured. Now let's move on to data analysis. Independent sample t-tests were run for each test. Additionally, an alpha threshold of 0.05 was implemented, meaning that if the p-value discovered was below this alpha threshold, there is a statistical significance between the values. IBM SPSS was used to conduct statistical analysis. The results for the thermal hardness analysis can show that in terms of ABS, the mean was 0.9567, and for PATG, it was 0.8567. This was measured in terms of hardness units, and the p-value was below 0.001, which is far below the alpha threshold of 0.05, indicating there is a statistical significance between these values. And it also goes to show that ABS performed better than PATG did within this test. In terms of the same thermal resistance test in the cold variant, a mean for ABS was 0.7122 and for PATG was 0.7400, and the p-values are 0.058 and 0.064, which is in fact above the alpha threshold of 0.05, indicating no statistical significance between these values, meaning that in terms of cold temperatures, no plastic was better suited than the other. In terms of the abrasion test where mass loss was measured, ABS had the average mass loss of negative 0.3249 and PATG had mass loss of negative 0.0630, and the p-values were below 0.001 and below 0.002, which is again far below the alpha threshold of 0.05, indicating there is a statistical significance between these values, but PATG performed better than ABS did and lost less mass on average. In terms of the water absorption percentage test, ABS had an average percentage of 0.8133, whereas PATG was about 1.4667, and the p-values were below 0.001, again far below the 0.05 alpha threshold, indicating a statistical significance between these values, also indicating that in terms of water absorption percentage, ABS absorbed less water on average and is better suited in terms of being in water. The next tests that were conducted had results that were non-normal. For example, a standard deviation of 0 was achieved here, and that's why an independent sample's t-test was not able to run. The number of drops was measured here to see how long it took to deform each prosthetic. For ABS, for each trial, it took 4 drops. For PATG, for each trial, it took 3 drops, showing that ABS on average survived longer than PATG did. Again, for the tensile strength test, where only 3 trials were conducted, ABS for each trial went displaced in horizontal millimeters by 5, 4, and 6, and PATG displaced by 25, 23, and 22, which is a wide difference, showing that in terms of tensile strength, ABS displaced a lot less than PATG did. In terms of a conclusion, overall, ABS is better suited for knee socket prosthetics because of its overall higher material durability. A key finding is ABS in the tensile strength test only displaced about 5, 4, and 6 millimeters, where PATG displaced about 25, 23, and 22 millimeters. Also, ABS was better suited in terms of warm temperatures and water absorption. In terms of some implications, PATG is better suited for flexibility purposes. As we saw in the tensile strength test, PATG displaced a very, very high millimeter amount comparative to ABS. But that goes to show how a blend of both ABS and PATG would revolutionize the industry of prosthetics, because PATG has a lot of flexibility capabilities and ABS has a lot of material durability structural capabilities. And in terms of things like knee sockets, where not only is material durability and strength durability needed, but also flexibility durability is needed, because that's what knees deal with a lot. Thus, a blend of both of these plastics could in fact revolutionize the field of knee socket prosthetics. For some limitations of the study, this study only examined lower limb knee socket prosthetics, not all prosthetics. For example, the results of the study cannot be generalized to arm prosthetics, face prosthetics, or torso prosthetics. Another limitation was the sample size. The 3D printer within the high school laboratory simply was not fast enough, nor the capacity to support a large sample size. Additionally, the filament costs of ABS and PETG hindered the sample size as well, meaning that if this study was replicated hundreds of times over and over again, different results could be achieved for few of the tests. In terms of future research, a comparison of various different types of filaments for various different types could be done. Essentially the same study, but on a much larger scale, because there are hundreds of different types of 3D printer filaments, from carbon fiber to PLA to biodegradable PETG and ABS. All of these different filaments could be compared against each other to see which filament is actually the best in terms of overall material durability for 3D printed prosthetics. Additionally, that same study could be replicated for different types of prosthetics to see for each type of prosthetic what is the best material suited. Lastly, future research could be conducted that examined the environmental factors and also factored in skin temperatures. The reason why skin temperatures is important because prosthetic users are actually going to be wearing these prosthetics. So it's important to see how the skin could actually impact the overall material durability. And environmental factors could obviously affect material durability. For example, each prosthetic could have different environmental susceptibility in terms of being in the sun or being in the cold, being in the snow. That's why environmental factors is something really important to look at. Let's look at some references. Thank you.